Hi guys, Miss O'Connell here. So this video is going to be a little bit fast. I need to get this up for you guys, and I had a carpet beetle infestation in my house, so it's been a little bit of a crazy 2 days here. So I'm going to go a little fast through this video just so I can get it up for you guys, but feel free to pause to take notes or refer back to it. Okay, so let's pause and give this do now a try. Okay, so this do now is a great way to start out the discussion for today. So as we know, the AP exam has moved more conceptual, so I'm going to try and use more conceptual examples to help us move forward the best that I can. As we know, physics isn't only conceptual, so we will need to apply some math or equations in here. So which of the following are characteristics of energy? So thermal energy can be changed to mechanical, mechanical can be changed to thermal, energy can be stored, energy has the ability to do work. So we might not know for sure that D is an answer choice, but hopefully from watching the videos from last week, we kind of came to that conclusion. So energy is the ability to do work. It's very difficult to define energy as it's as fundamental as space and time. So it's very difficult to define something that fundamental, but energy can be transferred. Okay, so A and B are correct. Energy can be stored. C is accurate, and energy allows the ability to do work. So D is also an answer choice. So your answer here that you should have came up with is E, all of the above. These are all characteristics of energy. Okay, and we know that energy has the ability to do work. So let's conceptually review what work is, and then elaborate on what positive and negative work mean. Okay, so work, there's an issue here with my slide animation, but that's okay. We're going to keep going. So if the force and displacement are in the positive direction, the same direction, then we say that the work done is positive. So we know that work is a force applied over a displacement. If the direction of the displacement and the direction of the force are in the same direction, we say that positive work is done. Okay, if positive work is done, the energy of the object will increase. So energy is added to the system when positive work is done on the system. Okay, if the force acts in the opposite direction to the displacement, so the displacement of the object and the force applied are in opposite directions, the work is considered to be negative. Okay, so if work done is negative, energy is taken away or decreases in that system. Okay, if the object is not displaced, then no work is done. If the displacement of the object and the force are perpendicular and not parallel, then no work is done. So in the example from last week with the waitress carrying the tray, right? When you carry a tray across the room, the force you're applying on the tray is up. The displacement, right, would be in the X. So if the force is in the Y and the displacement is in the X, there's no work done by that force. Okay, work is a scalar. So I know that we're saying that positive or negative work is done. Work itself is a scalar quantity. So that positive and negative sign do not mean direction. They are not associated with direction. Work has only magnitude, no direction. It is a scalar. Okay, but it can be negative. So it's one of the only scalar quantities in which we associate it to being negative. Okay, and the units that we have for work are joules, named after the thermal chemist who discovered that mechanical energy can be changed into thermal energy. Before his work, we really had no idea. We thought that energy disappeared. He is the one who realized that thermal energy is a type of energy and that energy is conserved. So that's why the unit is named after him. So units for energy and for work are joules. And just a reminder, right, a joule is a Newton times meter, or Newton times, or kilogram times meter squared over second squared. Okay, those are equivalent dimensions for a joule. Okay, so if you end up with newtons times meters, it's a joule. Kilogram times meters squared over second squared, it's a joule. Okay, so let's just review what we know about work. So we know that the force is not constant, that the work is equal to the integral of the force as a function of displacement. Right now we're focusing on constant forces. So if the force is constant, right, you take force times the displacement times the cosine of theta. Okay, theta is the angle between the force and the displacement vector. Okay, so let's talk a little bit more about positive and negative work. So to do that, we need to examine how force and work are related. So if we apply, similar to the suggestion with the waitress carrying the table, or the tray, if the force is applied perpendicular to the block, okay, and the block is still displaced, delta x, if we take our work equation, work equals force times delta x times the cosine of theta, regardless of what the force is and the displacement, when you multiply by the cosine of theta, you get 0. So if the force and the displacement are perpendicular, there is no work done by that force because that force does not cause a displacement. Okay, so let's take a look at a positive force. So let's say that there's a positive force applied to this block. That force causes a positive displacement. So force and displacement are parallel to each other. They act in the same direction. We would say, right, that the force causes positive work over displacement. So positive work is done. We can prove that, right, because when you take the cosine of 0, which would be the angle between the force vector and the displacement vector, we would simply get force times delta x, which would be a positive value. If we flip the direction of that force, so let's say that the force is pointing to the left, so causes a leftward force, but the displacement is technically to the right. So in this case, right, it's most likely not a tension or an applied force in which the displacement and the force would be in opposite directions, but what force causes a positive displacement but acts in the opposite direction? Hopefully we're thinking friction, right? So friction can act to the left, but the object can still have a displacement to the right. Okay, so the angle between these two vectors is technically 180 degrees. When we take the cosine of 180, we get a negative value. So technically negative work would be done on the block because the force and the displacement vectors point in opposite directions. Okay, so hopefully that mathematically makes a little bit more sense now. Let's apply this to a few examples that we might see on the AP exam. Okay, so we're going to focus a little bit more conceptually here. So in which of the following cases is positive work done by an external force? So as we read these, we need to think about first, what is the direction of the force? What is the direction of the displacement? Are they in the same direction or the opposite direction? If we want the positive work, right, the forces and the displacements should be in the positive direction. So a softball that catches a ball in her glove. Okay, so if you think about a baseball hitting a glove, the displacement of the ball would still be forward, right, to the right. But the force applied to stop it would be opposite to its displacement. So here's our displacement vector. The force applied by the glove would be in the opposite direction in order to bring the ball to a rest. Okay, so these force and displacement are opposite directions, so work done would be negative. What about a homeowner pushing a lawnmower from rest? So you push a lawnmower, right? The force would be forward, right, in the positive direction or to the right. The displacement would be in the same direction. Okay, so positive work is done. The force applied and the displacement are in the same direction. Work done is positive. All right, so we know that B is the answer, but let's continue here. Practice analyzing direction of force and direction of displacement. When a driver applies a brake to his car, okay, the car is going to continue to move forward, while the brake applies a force in the opposite direction of its motion. So force and displacement are opposite direction, so work done would be negative. In D, a student holds her textbook and it is not moving. If it is not moving, there can be no displacement. If there's no displacement, there's no work done. E, a ball falls from a height, the ground pushes or applies a force to stop the ball. So the displacement of the ball would be delta x, right, towards the ground, so in the negative direction. The force applied from the floor onto the ball would be in the positive direction, opposite its displacement. So work done in this situation would also be negative. So our answer here is B. Okay, let's take a look at a paragraph type response question. An athlete is holding a football. He then throws it to a teammate who catches it. Describe the work done on the football by both players, starting from when the football is at rest before it is thrown to up until after it is caught. Okay, so let's think about before it's thrown and after it's caught. Because in both of those situations, the ball is at rest. When the ball is at rest, it is not moving. So if the ball is not moving, it has no displacement. If it has no displacement, there is zero work done. So our first formulation here would be before the ball is thrown and after the ball is caught. It is at rest, meaning there is no work done because the displacement is zero. Okay, let's think about when it's thrown by the thrower. So think about direction of displacement, direction of applied force from the thrower. The displacement and the force will be in the same direction. When the ball is thrown, the displacement and the force applied are in the same direction. So positive work is done by the thrower on the ball. When it is caught, right, the catcher is bringing the force to the ball to rest. So that applied force is the opposite direction to its motion. So the ball is received by the catcher, the force applied to the ball by the catcher, and the displacement of the ball are in opposite directions. So negative work is done by the catcher. Okay. So we're going to take a look at work and energy. Okay, so we have a relationship for it, which we'll get to in a second. Work is done on the system, then energy is transferred to the system. Okay, so when the displacement and the force applied are in the same direction, there's positive work, and the energy of the object increases. So thinking about the baseball, right? The ball is given kinetic energy when work is done, positive work is done on the system. Work done by the system, okay, means that negative work is occurring. Energy is transferred from the system. Okay, so energy would decrease. So in terms of the thrower, applying a force that is in the opposite direction to the displacement is going to decrease the energy, the kinetic energy of the baseball. It'll go from some value to rest. Okay, so the equation relationship that we used for this is called the work kinetic energy theorem. We use this version of it for a constant force. Okay, so if the net work is positive, then kinetic energy is going to increase. If the net work is negative, then kinetic energy will decrease. Okay, it's added to another object that's outside of the system. So energy is still conserved, but energy in that system will decrease. Okay, and if there's zero work done, the object will move at a constant speed, so kinetic energy will not change. Let's take a look at how this applies to positive and negative work. So basically, we derive this equation by using the third Big Four equation in combination for the definition of work. Okay, so we determine here that work is 1/2 mass times the final velocity squared minus 1/2 mass times initial velocity squared. So basically, work is equal to the change in kinetic energy. For positive work, right, that is exactly true. Net positive work applied to a system increases its kinetic energy. So work is equal to the change in the kinetic energy of the system. When work is negative, we're going to take this equation and plug in a negative sign for work. So again, yes, work is a scalar, but negative work can be done if energy is released from the system. So if we make this negative, we're saying that negative work is equal to the change in kinetic energy. Rearranging this here, we say that the final kinetic energy is equal to the initial kinetic energy minus work done. So if work is negative, the final kinetic energy must be equal to the initial minus any work done. Okay, so if negative work is done on the object, its kinetic energy decreases, so the final velocity will be less than the initial velocity. Okay, let's try this in an example. So we're asked how much net external force must be applied to an object such that it gains 100 joules of kinetic energy over a displacement of 20 meters, parallel to the direction of the external force. Okay, so we know that work is equal to the change in kinetic energy. We're told that it gains, so there's a positive change in kinetic energy of 100 joules. So final minus initial kinetic energy will be 100 joules. The displacement occurs over 20 meters, and it's parallel to the direction of the external force. So what does that mean? That means that the work done is positive because the force and the displacement are in the same direction. So you know that this is positive. To find that force, we need to plug in what we know as the definition of work. Okay, if the force and the displacement are parallel to each other, we know here that we can substitute in F times delta theta, okay, because cosine of 0 would give us 1. So now we just plug in our values here. We have 100 joules. We don't know our force applied. We plug in 20 meters as our displacement. We divide both sides by 20 meters to get the applied force by itself, or technically the net external force. Could be a combination of forces. Okay, so net work equals change in kinetic energy. It could be technically a net force or an applied force. Doesn't exactly matter here. And we get 5 joules divided by meters. We get kilogram meters squared over seconds. So we would get newtons. So that final force applied would be newtons. Okay, so over spring break, there will be optional test prep that you can do in classroom. I'll post it tomorrow, Friday. It's optional, you don't have to do it. I won't be checking it, but I suggest highly that you do it. Every day that you don't solve a physics problem, the more information that you will lose. Okay, to retain it, you need to continue to use it. So I put some test prep up into classroom. It'll be there on Friday. I suggest that you do it, but you do not have to. You're not obligated, and it won't be graded. Enjoy your spring break, and I will talk to you next Monday, the 20th.